we're going to be talking about extreme values in this lesson. Basically, we're going to talk about first absolute extreme values. We have talked about this before in pre-calc, right? Absolute min, absolute max. Okay? So suppose you have a function with a domain of D. Okay? All right. We say f of c, the y value at c, is the absolute maximum value on that interval, right? On that interval, if and only if, on that interval, f of c happens to be the largest number compared to all the other ones. So for example, if on that interval, f of c is greater than or equal to all of the other f of x's, then it's the absolute maximum value. Yeah.
Does that mean that we won't know if we're getting the absolute minimum or the absolute maximum because it depends where f of c is?
Right. You'll see once we, yeah. And then how do we define absolute minimum? Something is defined to be an absolute minimum value, value meaning the y coordinate, right? If f of c is less than or equal to all of the other y values in that interval, okay? All right, so take a look here. Look at what's given to us here. On the interval negative pi to pi, you see how we're given a concrete closed interval. Find the maximum and minimum values of the functions. So we already know this. Here there is a maximum, right?
And then on the other side,
Yeah, so the x value there is pi over 2, and the y value is 1. So the way I write it is f of pi over 2 is equal to 1. And I know somebody's going to ask, do we have to write it that way? The answer is yes, because I want you to give me the x and the y values together.
how do we know it's halfway?
Well, because it goes from negative pi to pi, and that's halfway.
That's marked out about halfway.
And then here, this is f of negative pi over 2 equals negative 1. That's the minimum. Okay, now, here, there is a maximum, right? F of 0 is equal to 1. And then there are minima at negative pi and pi. Look at the y values. They're both equal to each other. So they're equally, minimum values. So here, I say these are the minima. So it's f of negative pi equals negative 1. F of pi equals negative 1. Okay, so that's pretty much pre-calc, okay? Well, this stuff too is pretty much pre-calc. So here we go. We want to find the absolute extrema of the same function, but on different domains. First, the domain is negative to positive infinity, all real numbers. So now we just have a parabola on all real numbers, okay? Well, let's do the minimum first. Here we have a minimum. That is the absolute lowest y value of that parabola. That's the absolute minimum. So I say f of 0 is equal to 0 is the absolute minimum. Now, on the interval negative to positive infinity, this parabola stretches upwards the whole time, so there is never a point where it maxes out. So there is no absolute maximum. So we say none on that interval. But now,
I was going to say, would you say D and E or
just no, none, not D and E, none. I mean none. Okay. Okay. Next, we are going from the interval 0 to 2. Starting at 0, going to 2.
Oh, I see what they're doing here.
Okay. So listen, we're going to ignore the right part of this. On that interval, the lowest possible value is 0. So I say absolute min, f of 0 is 0.
The bracket includes.
Right. The absolute maximum, look, if you just take that chunk, this is the highest point that the value, that you attain. So f of 2 is equal to 4.
What about f of negative?
No, that's not in the domain. Okay, negative
Oh, yeah,
2 is not, okay.
right, right.
So next, it's f of 0 open circle to 2. So the absolute maximum, it's still f of 2 is equal to 4. But now here, because it doesn't include that point,
None.
there is no absolute minimum because it never hits a point that's the lowest. Okay? Yeah.
You couldn't even say like 1 point or 0.01.
Right, but is it 0.01 or is it 0.001 or is it 0.1 or is it, you know? So that's the thing.
Like the limit as
Right, but there is no limit. There is just not an absolute minimum, okay? And then here, when they're both open, it's none for both. Okay. Now, okay, extreme value theorem. This is a big one, guys. It's otherwise known as EVT.
Oh, that's why you
Okay? Extreme value theorem, EVT. Now, this is going to pop up all the time. Okay? So let's make sure that from now, we make sure that like we have it down. You have to know when to use it and how to use it. So, here we go. If f is continuous on a closed interval, that's the important part, closed interval AB, then f has both a maximum and a minimum value on the interval. Okay? So you use the extreme value theorem when you have to find, so use to find absolute max or min on closed interval. If you have a closed interval and you need it to find absolute maximum and you don't use the EVT, 0 points. Okay? All right. So, yeah. Yeah. Okay, step 1, we need to find the critical points. And now you're asking, but what are the critical points, Ms. Malikian? Well, let me tell you. The critical points, okay, first of all, are points in the interior of the domain. We'll come back to that. These are points where one of two things happen. Either f prime is 0 or f prime does not exist. Okay? So to find critical points, it's either a point where f prime is 0 or f prime does not exist. Once you find your critical point, you've got to make sure that the critical points are in the domain. Okay? All right. Next, evaluate f of x where at each critical point and both endpoints. Okay? Step 3, this is the easy part. The largest value is the absolute max. The smallest is the absolute min. Okay. So, summarizing. Extreme values will only occur either at critical points or at endpoints. So let's take a couple of examples and see where exactly do extreme values happen, right? Take a look at the first one. You have a maximum here. What's happening here? There is a horizontal tangent. So f prime of x is equal to 0, right? There is a minimum here, but again, it's where f prime of x is equal to 0, correct? Both of these, if the domain is from A to B, both of these are in interior points, okay, like within the interval. Okay, take a look at this next one. There is nowhere where the derivative is equal to 0. There are no horizontal tangents, but there is still an absolute max and there is still an absolute min. Because it's a closed interval, those happen at the endpoints. Okay? So, and then, yeah.
So f prime wouldn't have to equal 0 or not exist there.
Right. Either at the critical points or at the endpoints. Take a look here, right? It could be any of the configurations. So look, you have max or min where the derivative equals 0, right? But take a look at this one. You have a maximum at a critical point, but the minimum is at an endpoint, right? So this is at a CP, but this is at an endpoint, right? So any combination can happen is what I'm trying to say, okay? Yeah. Yeah. Okay, now.
The top of a prime equals fx equals 0, right?
Right. No. Which top?
Number 3.
This, yes. Okay. All right, enough talking about when it can happen. Let's just find some, okay? All right. Use analytic methods, meaning like do some math, okay? To find the extreme values of the function on the interval and where they occur. So you're looking for two things. You want to find the extreme values and where they occur. So this is the y coordinate. This is the x coordinate. Okay? Value is always y. Where is always x. Okay? Okay. All right. So here we go. Okay. First, let's determine the domain. This is a polynomial function. What's the domain for all polynomial functions all the time?
All real numbers.
All real numbers. Domain is all real numbers. Because when you find the critical point, you want to make sure it's within the domain of the function. Okay. Let's find critical points. These are where the derivative is either 0 or undefined. So first, let's find the derivative. This is why we learned chapter 3 or 4.
Negative 2x.
Thank you. We're going to set this equal to 0. So how much is x? 2. This is your critical point. This is where f prime of x is equal to 0.
Oh, so it didn't have to be just like 2, but you could have x and stuff.
Yeah, no, well, like you solve it and then x equals 2.
I thought whatever you got, like if you got, let's say like you got like 5, that was just your equation, like x equals 5.
Right.
Since the derivative of 5 is 0, f of x, 5x equals 0.
That's exactly what it is. So like the critical point is at 2, so f prime at 2 is 0. Okay, so now we need to find absolute max or min, and we're given a closed interval. So we need to use the extreme value theorem. Okay? To do that, we evaluate f of x at the critical points and the endpoints. Okay? So that means I'm going to take f of x, the original printed f of x, and first I'm going to find f of 2, because that's my critical point, and then I'm going to find f of 0 and f of 3. Okay? Critical point, endpoints. Cool? Why are we doing this? Because it's a closed interval and you've got to use the extreme value theorem. Later on, deep into the year, you're also going to actually explicitly write using the EVT, blah. Okay, let's go. F of 2, I put 2 in here, negative 2 squared plus 4 times 2 minus 5. what am I doing here? I want to find what the y values are at these points so I could see where it's highest and where it's lowest. Well, this gives us -1. F of 0, -5. F of 3, -2. It's like Throwback Monday, back to algebra, right? Okay. All right. So take a look. The y values are -5, -2, and -1. This is the lowest y value, so that's the absolute min. This is the highest y value, so it's the absolute max. So how do you write your answer then? You say f of 2, oh, no, hang on, let me do it this way. You say absolute max, f of 2 is -1. Absolute min, f of 0 is -5. The derivative to equal 2/3 x to the -1/3, just like in chapter 4. Okay, for these things, I like to write them in root form. So this is going to be 2/3 cube root of x. The reason why I like to write it that way is because it's visually easier for me to see what's going on. So we need to find critical points. First, see where it equals 0. So f prime of x is equal to 0. Does it equal to 0 though?
No.
No, because let me tell you why. I'll only do this one time. If you set this equal to 0 and you cross multiply, you get 2 equal to 0, and that's not a thing, okay? So it's not possible. No, because critical point is either where it equals 0 or where the derivative is undefined. So is f prime of x ever undefined?
Yeah.
Where? Where is this undefined? At x equals 0, because that's where the denominator equals 0. So what we're going to do here is we're going to set the denominator equal to 0. So x is 0, that's the critical point. So how do you find critical points? It's where the derivative is 0 or undefined. So there can be one possibility of how to find a critical point, or there could be two possibilities of, there are functions where each of these could generate a critical point, and that's okay. We're not gonna what's the word? Discriminate, right? Okay. So okay, so let's do this. What are we doing here? Okay, EVT. We're going to do f prime at 0, f prime at -2, f prime at 3, 2, 3. Okay, f prime at 0, I'm sorry, not f prime. Sorry, f of 0. Oh my gosh, Miss Maliki. No wonder, it wasn't okay. So f of 0, 0 to the 2/3, that's just 0. F of -2, that's cube root of -2 squared, right? I'm plugging it into the printed one here. Cube root of 4. This is cube root of 3 squared, cube root of 9. Well, no, it's the cube root of 9. So, and I don't have a calculator, but that's fine. I don't need a calculator to realize that this is the minimum at 0, right? And this is the highest value, absolute max. So as the answer, I would write absolute max is f of 3 equals cube root of 9. That can't be simplified any further, so that's good enough. Okay. Oh, e to the x, e to the negative x. All right, so take a derivative. Negative e to the negative x. Yes? Okay. Now, what is this? This is negative 1 over e to the x, right? Okay. Is f prime of x equal to 0? When you set this equal to 0, you'll get 1 equals 0, which doesn't make sense, so it's not. Is f prime of x ever undefined? So for it to be undefined, e to the x would equal 0. Is e to the x ever equal to 0? It's not. E to the x looks like this. Okay, there is a horizontal asymptote here. So this denominator, e to the x, is never 0. So f prime of x is never undefined, since e to the x is never 0. What does that mean? There are no critical points. And hey, that's okay too. So what's left for us to do? Endpoints only. So f of negative 1 and f of positive 1. Okay, f of negative 1, e to the negative 1, e. F of 1, e to the minus 1, 1 over e. So, max and min, okay? So this is the absolute max, and this is the absolute min.
So you cannot determine, so let's just say, just quick, if a problem did have a critical point.
We talked about absolute min or max. Let's talk about local min or max. In pre-calc, we call these relative min or max, right? Relative extreme values. So this is a graph that goes from A to B, a closed interval A to B, that has 1, 2, 3, 4, 5 minima or maxima, okay? So there are 5 total extrema, okay? Of those, some can be absolute min or max, and others can be local or relative min or max, okay? So, take a look at this one here, at point A. On this interval A to B, this is definitely the lowest y value that the graph attains, correct? So that is the absolute minimum value, okay, from A to B. Okay, here you have another minimum, right? But this is a local minimum value.
It's a relative minimum.
It's exactly what it is. It's relative. Okay. Now, if I were to take like just this area here, this absolute minimum can also be a local minimum in its neighborhood, in its vicinity. Okay. So take a look at what we have here. This is a local maximum, correct? Why is this a maximum? This is where what has happened. There's a horizontal tangent there, right? F prime of x is equal to 0. Take a look at this for a minute. Is this a point where there is a horizontal tangent?
No, but it's undefined.
What is undefined? The derivative is undefined here. You see that this is where f prime of x is 0. This is where f prime of x is undefined. Because look, the slope from the left and the slope from the right are not equal. It's a corner.
I meant to say corner.
Okay? Yeah. All right. So what are local extreme values? You can get a local maximum value at a C if and only if f of C is greater than the other y values in some open interval nearby. Okay? You can get a local minimum if f of c is less than the other y values in a local, in an open interval nearby. Okay? All right. Okay. Okay, so let's take a look at this one. This one, we're going backwards. If a function f has a local maximum or a local minimum value at an interior point, and f prime exists, then f prime of c must equal 0. Let's think about that for a minute. F has a maximum or minimum in an interior point. So it's not an endpoint. It's one of these interior points. And f prime exists. So the derivative is not undefined. That means there is only one possibility that there is a horizontal tangent there. Okay, that f prime of c is equal to 0. All right, this is important. Why is this important? Because often they'll give you a certain situation and they'll say which of these is true. And one of the choices will be there is a horizontal tangent, blah, 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 blah. Right, Ari? You're with me? Yeah? Okay. Okay, let's move on. We did absolute min or max. Let's see how we find local extrema. Okay? A lot of the steps are the same. First, find the domain. Okay, we find the domain. Then, find the critical points, right? Same as before. Make sure the first steps are the same. So far, yeah. Now, here's where things change. Because it's an open interval, what we have to do is create a number line for f prime of x. Highlight that, for f prime of x. We need to put on here critical points and endpoints. And then sometimes, like, we can put open circles where the graph doesn't exist, so we know what's happening. That's for our own bookkeeping. Okay, using the number line, we need to test values within each interval. We did number lines in pre-calc honors, so you guys know how to do it. What you have to be careful of is you have to plug it into f prime of x. These are, I'm circling them in the same color for a reason. And then you put pluses where you get a positive, minus where you get a negative, same old number line as we've done before. But what does it mean? This is for f prime. What's f prime? What's the derivative of something? The slope. And if f prime is positive, if the slope is positive, what does it mean about the function? It increases. Gavi's going like that, so it increases. So when f prime changes from positive to negative, there is a maximum. Minus to plus, there is a minimum. Okay? All right, let's do one. Okay. Extreme values where they occur. What's the domain here? All real numbers. That's the domain. Okay. Now, take a derivative, find the critical points. Let's do this. F prime of x, 3x squared minus 4x. Oh, 6x plus 3. I'm going to factor out a 3. Okay?
Always set the denominator equal 0.
There is no denominator here. So 0 equals 3x squared minus 2x plus 1. The 3 divides out. So let's factor. This is x minus 1 squared. So x equals 1 is a critical point. Yeah? Yes. Okay. Now, we found the critical point. Step 3, create a number line. Let's create a number line. This number line represents my domain. And I like to put here that this goes from positive to negative infinity, so I know. I put on here all critical points. In this case, I only have one at x equals 1. What I also want to do here is I like to write down or note that this is for f prime. Because now we're going to do what we used to do in pre-calc. We have two regions here. We're going to plug values into f prime. And you can plug them into here. You can plug them into here. It really doesn't matter. Here, we're going to put it in here. So if I have x equals 0 from the left-hand side of this region, right? 0 in here, you square it, you get positive. A number greater than 1, you put it in there, you get positive again.
So what
Because
if
it's squared.
If it doesn't change, then is it?
So what does this mean?
Is it the minimum?
No, because look, what does this mean about f? If the slope is positive, what does it mean about the function? Increasing, increasing. This function is continuously increasing. So there is no max, nor is there a min. Okay? So there is no extreme values. No, because it goes down to infinity. So like, it's right. So it's like at negative infinity, it's just like climbing up. Just like for the parabola, there was not an absolute maximum at the very top, was there?
No, but at x equals 1.
At x equals 1. So this is an x cubed graph. So it probably, you know, just, there is,
both ways,
yeah.
The square is 0 x minus 1 squared, it's going to be positive.
Right.
That makes sense.
Yep. Okay. So let's do another one.
What would the final answer be?
That's it. No min or max.
No min slash max, so no.
Okay. So this one, we're going to take a derivative.
Got it.
Hello, chain rule. Yes. Yes.
Hooray.
Let's write it like this. Huh? Yeah, we do. Let's write it like this. Okay, we need to find domain first. Okay, here's how we find domain. When you look at 1 over the square root, right? So as far as the domain is concerned, we need for this argument, 4 minus x squared, to always be positive. Okay? So I'm going to do 4 minus x squared greater than 0. Notice it can't be equal to 0 because then you'll have 1 over 0. So when you factor this, 2 minus x, 2 plus x, greater than 0. Now I need to figure out in which regions this is going to be positive. Well, I have a 2 and a negative 2, right, when I solve for these? Okay, if I have numbers greater than 2 and I plug them in here, do I get positive or negative? Greater than 2. Negative, so that's not going to work. If I have numbers less than negative 2, what am I going to get? Negative again, yes? Like if I had, like if x is negative 5, then I'm going to get 2 minus 5, so it's going to be negative again. So the only regions which work is between negative 2 and 2. So the domain is negative 2 to 2. Okay, now let's take a derivative. F prime of x is the negative half comes down. 4 minus x squared to the power of what?
Negative 3 over 2.
Times the derivative of the inside, which is negative 2x. Okay. Negative 2 cancels with negative half. F prime of x is equal to, okay, I have x on top here, x. I'll color code it. And then this goes to the bottom, so it becomes the square root of 4 minus x squared cubed. Okay? All right. So Let's see, where is f prime of x is equal to 0? So we're going to take this whole thing, set it equal to 0. You cross multiply, x is 0. Okay? Now, is f prime of x undefined anywhere?
Yeah.
We're going to set the denominator equal to 0. Okay? Notice for the denominator, like the root and the cube root, they go away. So it's just like the filling equal to 0. X is plus or minus 2. Okay. I got critical points. I got my domain. Let's do a number line. The number line should represent the domain. Your domain goes from -2 to 2. So this is -2 to 2. But it doesn't include -2 and 2, right? So I like to put those parentheses just so I know. Okay, those are already part of the critical points. And then another critical point is 0. Okay, so this is f prime. So let's plug f prime. Let's plug values into f prime. Okay, let's do this. When I get numbers from this region, like -1, okay? Numerator gives me negative, okay? Denominator, 4 minus +1, so that's positive, okay? Negative over positive is negative. Should we do that again?
No.
Okay, you put -1 in here. You get negative on top. Here, -1 squared is +1. 4 minus 1 is positive, so negative over positive. I'm going to put 1 in here. +1 over a positive number, so that's positive. Which means the function is decreasing here and increasing there. So there is there is just a local min. We don't know if it's an absolute min. There is a local min.
Why do we have no?
So we say, because it's an open interval, so we're not sure.
Right,
Yeah.
right.
So the minimum is at f of 0 equal to 1 over, we're going to plug it, look, this is f of 0. So we plug it all the way into the original equation. 1 over root 4 minus 0, 1/2. Okay? All right, last one. Identify the critical points and determine the local extreme values. Okay, let's do domain first. Okay, this is a piecewise function. In the first function, I have a parabola, which means like no restrictions on domain. After x is 1, I have a linear function, no restrictions on domain. So I'm good before x equals 1, I'm good after x equals 1. What about at x equals 1?
You're so good.
Right, I plug 1 in there, y equals 3. I plug 1 in here, y equals 3. Same y value. It's a closed circle there. Continuous function. This domain is negative to positive infinity. We're looking good so far. Okay. Let's find the derivative, right? F prime of x is piecewise function will have a piecewise function as a derivative. The top function, when I take a derivative, gives me negative 4x. What does the bottom function give me?
1, 1.
Okay, same bounds, copy over. Okay, so we have to see where the derivative is 0 and or where the derivative is undefined. f prime of x is equal to 0, where you have to set each function equal to 0 independently. Well, negative 4x equal to 0, x is 0, so that's a critical point. Does the second function give you a critical point? It does not.
No, it's undefined at 1.
You also have to check where f of x is undefined. For that, you have to check for the derivative from the left and the right. So the derivative here is negative 4. The derivative here is 1. So you have a different slope, right? At x equals 1, that means it's undefined at x equals 1. That's another critical point. So here we have 2 critical points. Okay?
What was that point? You plugged it into...
Yeah, the derivative, I evaluated the derivative from the left and the right at x equals 1.
Okay.
Okay? Okay. So now, let's do a number line. This is going to represent the domain. And on here, I'm going to put all of the critical points. Okay? All right. So, this is for f prime. That means I'm going to plug values into their respective regions, right? Meaning, give me a value from here.
Negative 1.
Negative 1 it is. Where does it go? Top or bottom?
Top.
Top, so I get a positive value. 0.5, where does it go? Top or bottom?
Top.
Top, so what do I get? Positive or negative? Negative. Like 2, x equals 2, where does it go? Bottom?
Positive.
Positive 1. Function is increasing, decreasing, increasing. So I get a maximum and I get a minimum. Okay?
What about the second one?
That's it. There's a maximum there and a minimum there. That's for the whole function, over the entire life of the function. So I say there is a maximum, and it's f of 0 equals, now I'm plugging it all the way here. Look, no, I'm plugging it into the function, f of 0. So what's f of 0?
5.
And the minimum is f of 1, which is
You can't say this is absolute.
3. They're both 3.
You can't say this is absolute.
Correct. Okay. One other thing. So, does this make sense? What the heck is going on here, right? What is happening here? Let's see. Look at this function, right? The division is at 1. And look, before that, it's a parabola, right? That goes to 3. And then after that, it's a function. It's a linear function that goes up. Do you see that? Look at how beautifully, look at how it all meshes together. Look, that's the graph. If you graph it, like if you sketch the graph, that's what it looks like here. Okay? Parabola comes down, and then here, there's a corner. It's continuous. Okay? But this is a point where the derivative is undefined. And look, since there is a parabola here, there is a horizontal tangent there. I mean, can it get more beautiful than this? I mean, seriously though. What a way to end the day, like seriously. Right? Yes.
Are these made in macros or